Okay, everybody, so download the Grasshopper file Sunpath mapping on our course website and open it up to see this on your canvas. In order to generate the Sunpath, which is what we're going to do, we need to bring in obviously the weather data. So just copy your URL address, just like we did in the last couple of weeks. And you'll see over here that there's a component named Sunpath. And in order to generate a Sunpath, it's actually very simple. We just take the location and plug it in to the Sunpath. And soon after that, we'll see the Sunpath generated for New York, which is in the southern hemisphere. It has a latitude of 40 degrees, right? You'll see that the default position for any of the sun paths is December 21st at noon. So that's the winter solstice. We do need to adjust for magnetic declination. So you'll see over here the north arrow, the north input component. And we can add the true north vector to that. So we'll see most immediately that we'll see a declination of about, what is that? Magnetic declination of minus 12.8. So minus indicates a rotation to the west, right? So we're going to use the true north vector so we can see that declination applied. So that's pretty substantial. If we want to see the actual sun locations, so there's a sphere for every hour of the year, we'll have to adjust obviously what's showing up in terms of the duration. If you hover over, we'll see noon, right? 21st of December as the default. So in order to get it for the whole year, we can define an analysis period. I've defined that here as January 1st at 1 a.m. to December 31st at midnight. So we can plug that in there and we'll see each position represented for every hour. All right, so we have the sun path, and you can see the solar alemma for each for each hour of the year. Sometimes that can be a lot of data, and maybe we want to just pull out the winter solstice, the equinox, as well as the summer solstice above here. So another way to do that is to simply define the months, right? So I've put in here a preset panel of January, the equinox, September, and December. So that can be plugged right into the month period, and you'll see very quickly that this is showing it for the 21st of both June, September, and December at noon. We can further define that for the full day. So I've basically put in 1 to 24, which is a series into the hour. Now we can see the sun locations for the full day, from the morning to the evening for June 21st, March or September equinox, as well as December 21st, the winter solstice. The other things we can adjust obviously is a center point. You can set a point and move your Sunpath diagram if needed. We can also adjust the scale of the entire sun path, which will automatically scale up as well the suns. If we want to change obviously the size of the suns, we can plug that in. We get bigger. I'm just going to disconnect that. Too big. And the last thing we can do is to, right now we're seeing, if we go to perspective, that this is a 3D projection. Right now that's the default value set to 0, so it's a 3D hemisphere. But if we wanted it to either be represented in ortho or stereo as a 2D graph, we can set that to, so this we can see if we go to top view. So this has been flattened to a 2D Sunpath diagram. And this is a orthographic. So you can see over here that the actual spaces between the altitude angles are not equal, but we can easily choose 2, which is a stereographic representation, 2D representation, where we now see everything adjusted. What you can do to customize the Sunpath diagram is to customize the colors of the sun to reflect values coming out of our EPW file. So disconnect these and put in the full year in terms of the analysis period. And I'm also going to plug in, we'll just take dry bulb temperature for now, and plug that into the annual hourly data of the Sunpath component. The actual dry bulb temperature value is colored according to the scale. And that can tell us what the temperature is when the sun is at a specific location, right? That might be useful. But what might be more useful than dry bulb temperature is to take into account the outdoor comfort conditions. So we'll see over here in this component, calculation of outdoor comfort, 2 components that are really important, which is a outdoor solar temperature adjuster. This is commonly used in outdoor comfort studies, and takes into account a number of different inputs, including the solar dome, diffuse horizontal radiation, horizontal infrared, and that gives us a solar adjusted mean radiant temperature that can be used to calculate more accurately outdoor comfort. And so the different parameters that we looked at last week in terms of dry bulb temperature, mean radiant, wind speed, relative humidity, all the environmental variables are taken into account. And with that output, we can also, instead of plugging in dry bulb temperature into the annual hourly data, we can look at a few of these. So we've already got all of the key inputs plugged in, so you can see over here. And we're going to take the mean radiant temperature output and plot some of the outputs here. The Universal Thermal Climate Index is useful for sort of feels like temperature in quotation marks. So when we know, when we look at the weather of the day, it might be 72 degrees Celsius, but really when you go outside, it's 64 because of the wind chill or the relative humidity. So that can be plugged into annual hourly data. Comfortable or not really just gives us a Boolean value. So it might be, you know, blue or red. We also might have a thermal stress value ranging from -1 to +1 that just delineates whether we're stressed in terms of heat or cold. What we're going to use here, because this is a bit more useful, is the Fanger scale that we looked at last week, which tells us what the condition of the person on that 7-point scale from -3 to +3, with 0 being thermally neutral. So we're going to plug that in to annual hourly data. Great. So the results are here, and we can see that scale from -3 to +3. But because we have sort of more incremental steps of what looks like 0.6, we can adjust that with a legend parameter that basically just shows the numbers -3, -2, -1 by giving it 7 steps between those numbers. And we can also just plug that into legend parameters, and that will adjust our scale. So we have just those 7 points. Great. So now that we have our results, we can see over here in the summertime, as we approach the summer, we can see periods of heat stress in red, as well as in the winter time, actually majority of the year where we feel too cold outside. So these are a few ways one can customize your Sunpath diagram to show outdoor comfort or any of the output climate data variables